All right, this is Jack Jackson, and we're back with a section or video where we can see how to perform a hypothesis test for the difference in population means from two independent samples. In the last video, we looked at what happens if we have paired data, which is not really two samples, but really one sample of ordered pairs, or the one sample of differences. Here, we're going to look at two independent samples. Now, data measured from two independent samples from potentially different populations. Subscripts are used to identify parameters from each sample. If both populations are normally distributed, then the difference is D in the sample sample means will be distributed normally with D equal x bar 1 minus x bar 2. The mean of the D's is mu1 minus mu2. Standard deviation is given by standard deviation of 1 squared divided by n1 plus standard deviation of 2 squared divided by n2. Then add that up, then square root. Usually the population standard deviations are unknown and not assumed to be equal, so we use a two-sample test, non-pool version. These are the formulas that we have. The degrees of freedom is a rather complicated formula there, and we work this out. If we have data from independent samples from two populations with different standard deviations, then we have to use the non-pool versions of the test on the previous slide. If we're extremely sure that the two populations have the same standard deviation, then we can increase the power of the test, that is, decrease the probability of a type 2 error, by pooling the data all together to estimate the standard deviation of the differences of the means. Using a pool test makes the formula easier for degrees of freedom. It's just n1 plus n2 minus 1, but it makes the calculation of the estimated standard deviation harder. The calculator app lets you choose pooled or non-pooled estimates for the standard deviation and degrees of freedom. In this course, we will always use a non-pooled version for this test, mainly just to make it easier on you. All right, a study was performed to determine differences between diastolic blood pressure reading between men and women. The following table gives the summary statistics for two groups of subjects. We tested 13 females, got a mean of 71.08, standard deviation 9.22. Tested 16 males, got a mean of 77.37 and a standard deviation of 8.35. Is there sufficient evidence at the alpha equals 0.05 level to determine that there is a difference in the diastolic blood pressure reading between men and women? Compute a 95% confidence interval for the difference in diastolic blood pressure for females minus males. So females minus males, that means females is group 1, males is group 2 when we put it in our calculator. So just run this through your calculator. There is a two-sample t-test and a two-sample t-interval. Just run them. So we run this like this. Stat test, choose statistics. X bar is 71.08. That was given here. S is 9.22 and N is 13. That's the statistics for group 1, which is females in this case. Put in the same information, corresponding information for group 2, which is males. In my class, we're always going to choose not pooled, and we're just testing for, is there a difference? So that's a two-tailed test, so it's not equal. Choose calculate, and it returns this screen here. A T-star test statistic, degrees of freedom by that complicated formula, somewhat complicated formula. The X bar 1 and 2 are given along with the S1 and 2. Actually, we typed all those in the end, so we knew all that stuff. But what's new, main thing new and important is the p-value. Really, that's the main thing you want to get off that screen, which is a 0.068. Compare that to alpha of 0.05. In this case, that is larger than alpha, so there is not enough evidence to reject the null hypothesis. So look what's going to happen here. If we do a two-sample t-interval, we do statistics, and all that's probably going to be already typed in for you. Again, do a non-pooled level at a confidence level of 0.95. Go down here and hit calculate. And among other things, it gives you some statistics, but it also gives you that confidence interval. So there's a good chance that the males are less, down to 13, but there's a possibility the females are going up to 0.5. Could be actually an average difference anywhere in there, and notice that 0 is in that interval. This is typically what happens when we do not have enough evidence to reject the null hypothesis. So our conclusion is a two-sample, two-tailed t-test was performed on this data. The test produced a p-value of 0.068, so at the alpha equals 0.05 level, there's not enough evidence to conclude that there is any significant difference in diastolic blood pressure between males and females. I have 95% confidence interval for the mean difference, female pressure minus male, is negative 13.09 up to 0.51. Notice when we state our conclusion, it should include what type of test is used, the p-value from the hypothesis test, the alpha level, the conclusion, and the context of the problem. It is good practice to also include the confidence interval for the difference in means, especially if the null hypothesis is rejected. State the confidence level using the same alpha as in the as a two-tailed hypothesis test. All right, here's another exercise for you. You should do this one on your own. Selling prices of several homes were taken in two suburbs of Rochester, New York, as given in the table to the right, in Penfield and Perrington. Is there sufficient evidence at the alpha equals 0.05 level to determine that the selling price of homes in Perrington, was higher than in Penfield at this time? All right, you should be able to work this out. Do this on your own. Come back when you're done and check your answers against the slides here. Press pause now. Okay, you're back. I hope that means you tried this on your own. Let's check your work here. We perform a two-sample, two-tailed t-test. Well, why do we do that? These are not paired up in any way. We assume that these two samples really don't have that much to do with each other, that they are independent. So that makes sense why it's independent or two-sample. It's a t-test because we're comparing averages, comparing means, and we don't know the population standard deviation. So it's a two-sample, two-tailed t-test. Why two-tailed? Because we're just determining if it was different. Actually, no, it's not a two-tailed test. This one is a left-tailed test. Let me correct that. Okay, I made that correction as a two-sample left-tailed t-test. Why is it a left-tailed? Because we're trying to see that Perrington was higher than Penfield. Perrington is group 2, so group 2 higher than group 1. That's actually a less than. That means group 1 is less than group 2. So it's this less than or greater than is kind of from the perspective of group 1. If group 1, you're trying to show group 1 is less than group 2, that's going to be a less than. Group 1 is greater than group 2, greater than. Group 1 is just different than group 2, that will be not equal to. In this case, we're saying group 1 is lower, Penfield is lower than Perrington in their home prices. That's what we're testing. So it is a left-tailed test. That's why we choose this one right here. So get your data typed in as L1 and L2. Go to two-sample t-test, choose the data, L1 and L2, both frequency 1, left-tailed test. Always choose non-pool for my class. And we get this screen, which we could arrow down to get this last one. And most particularly, we get our P value of 0.09. It depends on what we're going to compare to. If we use 0.1 for an alpha, then there is enough to give us that conclusion that there is enough evidence to reject the null hypothesis. So we do have a strong enough evidence here to say that Penfield has lower prices than Perrington. So Perrington has higher prices than Penfield. So you should be able to do several problems of this kind, including 36 on homework set 4 in my current setup.